In this presentation, we organize 6 steps to graphing a rational function. In the textbook, the free textbook by Stitz and Ziegler, it suggests 6 steps to graphing a rational function. These steps are: find the domain of the rational function, reduce the function to lowest terms, find the x and y intercepts, if they exist, determine the location of any vertical asymptotes or holes in the graph, if they exist, and then analyze the behavior on either side of these asymptotes. Analyze the end behavior of my rational function, and as you do that, find the horizontal or slant asymptotes if they exist. Use a sign diagram and plot any additional points as needed to sketch the graph. Let's work through some examples. We're going to use the 6 steps to graph the rational function h of x here, which is a quadratic divided by another. If we factor the numerator and denominator, we can rewrite it in this way. The domain is the set of all real numbers except where the denominator is 0. In this case, x equals minus 2 will make the denominator 0, and x equals minus 4 will make the denominator 0, so those cannot be in the domain. So in interval notation, we see the domain written this way: essentially all real numbers except minus 4 and minus 2. The numerator and the denominator have no common factors, so h of x is already in lowest terms. So this means that there are no holes, no removable singularities in the graph. The y-intercept occurs where x is 0. Plug in x is 0, and you get that the numerator is minus 250 and the denominator is 8. Simplify that a little bit and see that the y-intercept is minus 31 1/4. To find the x-intercept, we set the numerator equal to 0, so we need to factor 10x squared minus 250. Let's pull out a 10 and notice that we really have x squared minus 25. That factors, it's a difference of squares, so it factors into x minus 5 and x plus 5. So 5 and minus 5 are the zeros, or the x-intercepts. So my x-intercepts are the points minus 5, 0, and 5, 0. Since my fraction is in lowest term, there are no holes, but the denominator factors this way, and so the denominator will be 0 when x is minus 4 or minus 2. So we have vertical asymptotes here. The lines x is minus 4 and the line x equals minus 2. As x gets large in absolute value, and so the graph moves far away from the y-axis, my rational function begins to look just like a 10x squared over x squared. Throw away the smaller terms, and 10x squared over x squared is the number 10, so a horizontal asymptote is y equals 10. We knew we would have a horizontal asymptote because the degree of the numerator was equal to the degree of the denominator, and that this horizontal asymptote could be found by looking at the leading coefficients of the highest terms. To draw the sign diagram, we use zeros, x equals minus 5 and x equals 5, and vertical asymptotes minus 4 and minus 2 to create our fences, and then test values between these fences. Here's the result. My fences occur at minus 5, minus 4, minus 2, and 5, and if I check out some values between them, like x equals minus 6, I get a positive value. Between minus 5 and minus 4, I get a negative value. Between minus 4 and minus 2, positive. Between minus 2 and 5, negative. Between 5 and to the right of 5, positive. So these are alternating in sign. So let's look at the graph. Here's the graph drawn in blue. The vertical asymptotes are in red, and the horizontal asymptote at y equals 10 is in green. One more example. Let's look at this cubic divided by a quadratic. Find all the intercepts and zeros, and then graph this function. So let's work through the 6 steps. First off, the denominator factors as x minus 4 times x plus 2, so the domain is a set of real numbers where the denominator is not 0, so it's these intervals that dodge minus 2 and 4. In other words, everything to the left of minus 2, union, everything between minus 2 and 4, union, everything to the right of 4. Notice that when we evaluate the numerator at minus 2, we get 0. So x plus 2 turns out to be a factor of the numerator also. So x plus 2 is a factor of both the numerator and the denominator. Recognizing that x plus 2 is a factor of the numerator, we can further factor the numerator using the techniques from an earlier section. We could do synthetic division with x plus 2, and discover that the numerator factors into x plus 2 times x minus 2 times 3x plus 1. So I have factored my numerator and denominator and rewritten my rational polynomial, my rational function this way. Now, x plus 2 is a factor of both numerator and denominator. That means that x equals minus 2 is a whole, a removable singularity. We can then put our rational function in the lowest terms and write it this way, just remembering that we cannot plug in minus 2 for x. The y-intercept is what we get by plugging in x equals 0. That turns out to be positive 2. The x-intercepts occur when we set the numerator equal to 0, and so these occur when x is 2 and when x is minus a third. We cannot have an x-intercept where we have that whole at x equals minus 2. We have a whole at x equals minus 2. And so looking at the reduced form, we see that when we plug in minus 2, if we were allowed to plug in minus 2 into the reduced form, we would get minus 10 thirds. So the graph is going to go through minus 2 comma minus 10 thirds. It's just we're not allowed to plug in x equals minus 2. And then there's one vertical asymptote, x equals 4. To analyze the end behavior of the rational function, we need to do long division because there's once I've reduced it, we have a quadratic in the numerator and a linear term in the denominator. And so my rational function now begins to look like the quotient 3x minus 2 plus the remainder minus 4 divided by x minus 1. And so there's an oblique or slant asymptote at that quotient where y is 3x minus 2. The sign diagram looks like this, directed by the zeros and vertical asymptotes. And so putting it all together, the graph looks like this. The slant asymptote is this green line. The vertical asymptote is the red line. And if I carefully graph my function, I'll see that it has the graph given in blue that approaches these lines in various regions of the plane. In the next series of lectures, we'll move on to a new topic, exponential functions and their inverse functions, that is, logarithms.